Hello, everybody, and welcome to On the Spot STEM. Today we will be tackling the USACO Gold January 2019 Cal Poetry problem. Now, initially looking at this problem, it throws a lot of information at us, so we need to break this problem down into individual components. So, looking at it first, we know that we have a bunch of words, and each word has a syllable count and a rhyme scheme, a rhyme class, as the problem calls it. And the poem that we make, we want it to have certain rhyming words, such as all words that have A rhyme with each other, all the B's rhyme with each other, and so on. Also, we see that we have to print our answer modulo 10 to the 9 plus 7. And usually when problems throw this at us, it means they want us to find a mathematical approach, because this number is way too large to count everything individually. So our first step can be to group words with the same rhyme scheme. So, for example, rhyme scheme 1 has a word with syllable count of 3 and a word with syllable count of 4. And rhyme scheme 2 has just one word with a syllable count of 3. So looking at this, we know that these words are going to have to make up our poem. And we want to find the number of ways to create lines such that each line has 10 syllables in it. Or it'll be K when we generalize it. So looking at this problem, we know that each word, and by word I mean like each A, each B, and each C, and so on, each one of those must correspond to a certain rhyme class, because all words with all the letter A's must rhyme with each other, all the letter B's must rhyme with each other, and so on. So we can think of this as the number of ways to generate like combinatorics to solve our problem. So we want to figure out the number of ways we can create word A, and then raise that to the power of the number of A's that there are. And what this does for us is this helps us generate the number of ways we can pick words to match the A's. And then if we use this process for the B's, C's, and so on, we can multiply all these values together to solve the problem. Now, how many ways are there to pick, let's say, the first A? So what we need to do is parse through every single rhymes class, because the word A could be the rhyme class 1, it could be rhyme class 2, it could be rhyme class 3. We need to consider all of these different possibilities. So what we can do is, let's say it belongs to rhyme class 1. So what we do is we want to figure out the number of ways to add up to 10. So let's say that word A corresponds to rhyme class 1. Well, what words are there in rhyme class 1? Well, there's a word of syllable length 3. So if we were to make this letter A be the word of syllable length 3, then that means we have 7 syllables left for the other words to add up to. So all this is now is trying to figure out how many ways there are for these words over here to add up to 7. Let's say we picked the word 4 with syllable length 4. And if we do that, well then, instead of adding up to 7, the rest of the words have to add up to a syllable length of 6. So the number of ways to do this, we have to find that using these words, and so on and so on. Now, if we just brute force try to figure out the number of ways we can add up to 6 or 7, this will get very, very lengthy in terms of time complexity. So instead, we can turn to our friend the dynamic programming approach and sort of store the number of ways we can add up to n. So where dp of n equals the number of ways we can add up to n. So now that we found this dp approach, we need to apply it with combinatorics to figure out the number of ways we can pick words to fill line A. Given the first line A, we know that we could pick the word with 3 syllables to be the ending, or the word with 4 syllables to be the ending. So all we have to do is calculate the number of different ways there are to do that, add them together, and then that represents the number of ways we could have a line that ends with a word of rhyme class 1. So now that we've figured out that, let's try to think about why this works. Let's look at this problem from the combinatorics aspect. So using the test case they gave us above, we have 3 lines. Okay, each line being A, B, and A. So what we want to do is, if we want to figure out the number of ways we can make this poem, we need to figure out the number of ways we can fill the first spot times the number of ways we can fill the second spot times the number of ways we can fill the third spot. And this is just based on combinatorics, the number of ways you can sort of form this sequence. So within each line, there's actually another separate combinatorics problem where we're trying to figure out how many ways we can choose the letters of A to rhyme with the same letter, with the same rhyme class. So let's say we assigned all of them to rhyme class 1. We need to figure out the number of ways we can end this one with a line that ends in rhyme class 1, and then square that because there's 2 A's that we could have ended in rhyme class 1. And then we need to add that to the number of ways to do that to 2, etc., etc., etc. So this definitely works mathematically, and using DP, we can make this work in programming. So let's look at an implementation of this code. As you can see, I've set up a lot of different input reading. So let's go step by step through the input just to make sure that we know what we're doing. So first off, we're going to be taking the answer mod 10 to the 9 plus 7. So it's always good to have a global variable that we can always just take the mod up. Second, each word has a syllable count and a rhyme class. So that's what I'm representing here with long S and long C. Over here, I have the input, the ways we gather input with the scanner, file, and print writer. And over here, I'm reading in the variables that we're going to be using. We have n words, we have m lines in our poem, and each line has k syllables. Now, over here, I use a hash map, 2 of them in fact, to store how many letters there are of a certain type. For example, I would have the character A mapped to the number 2, because there were 2 A's in that test case. And over here, I figure out how many words are in the same rhyme zone. So this first long will represent the rhyme class of the word, and this array list of longs will store the list of all the words, syllables that are in that rhyme class. So over here, I gather the input and add it to the first hash map that I made of rhyming words. And over here, I make a for loop that iterates through and adds the lines of the poem that we will be using. So to start off, let us create our DP array. And this will be the first DP array that represents the number of ways we can add up to n syllables given all the words that we have. And this is used to solve that mini DP problem within the larger DP problem. So first off, we have static int DP add. And I actually, instead of using int, I like to create everything as longs when it comes to these problems, because taking it modulo is a lot easier if you have a little more digits that you can store. So for starters, we create dp add equals new long of k, because there are only k syllables in a line. So if we put a word as the last word, there will be less than k syllables that we have to add up to. So k is a good number to store. And then we can use arrays.fill to fill in this dp-add array with long.maxValue. This is so that we know when we don't need to go through a branch of the tree that we have already gone through. And what we do here is a little neat trick where we set dp-add of 0 equal to 1. This is because if we want to figure out the number of ways to add up to a certain number n, if we are able to get to 0 from that n, that means we have found a way that we can add up to n. So let us start by making our add method, our dp ways to add. So static long dp ways to add. And what this will take in is the number of syllables that I need to add up to, k, and the array of words that we have created. So first off, if k is less than 0, That means we couldn't find any way to add up to this, so we return 0. And also, if dp of k is not equal to long.max value, sorry, dp add, then that means we have already come to this value and we don't need to recalculate this part of the tree again. So we can just return dp add of k and mod, we want to take it modulo just so we don't get any long overflow error. So let's create a value called store, which will store the number of ways we can add up to k, and that we can set the dp array of this value equal to later. So what we want to do is for every word in our array, we want to use that word as, and see if we could have added up if we use that word as our last move. So store plus equals dp ways to add of k minus r of I, and then remember r of I is an array of words, so we want to subtract the syllable count, and then we also want to pass in r because that's one of our parameters. And we also want to cast this to an int because remember it's a long and we're passing it in as an int. Secondly, we want to take store mod so we never get any overflow errors. This is really important because otherwise overflow errors can happen and you'll miss a lot of points that you would have gotten if you had accounted for it. Finally, what we do is we set our dp array equal to store, and then we return dp add of k. Now that we've solved this mini dp problem, let's solve the overarching dp problem of how many ways there are to assign each thing to a line. So what I did is I created a dp array called letter, dp letter. So what I want dp letter of 0 to store is the number of ways I can assign the a's. I want dp letter of 1 to store how many ways I can assign the letters a and b, and so on and so forth, because the number of ways I can assign letter a and b is the number of ways I can assign letter a times the number of ways I can assign letter b, which I can do very simply. So what I do is I want to parse through every letter I have. So for in I equals 0, I is less than 26, since there are 26 letters in the alphabet that could possibly represent our line. Now, first, what we want to do is make sure the letter that we're looking at is contained in the poem, because we don't want to look at a line that's not even in our poem, because we want to only assign for what we have. So if the char of I plus a, because this is the ASCII representation of the letter A that we would have stored as a character, we want to figure out the number of ways we can place words together so that they form this line of the whatever letter we're focusing on. So what we want to do is go rhyme class by rhyme class, because all letters have to rhyme with each other. All lines of type A have to rhyme with each other. So we can go rhyme class by rhyme class and figure out the number of ways we can do each one of those. So what we want to do is we want to iterate through our hash map that we made earlier by doing iterator it equals equals rhyme. That was the hash map that we made, entry set iterator. And then we do, to iterate through our hash map, we do while it.has next. And then we basically figure out the pair. This is basically Java's way of getting a hash map to tell us the first key and what it has as its value. And we access this by doing pair.key and pair.value. So we want to figure out the number of ways we could have assigned rhyme class 1. Like, let's say the first, so we're right now looking at rhyme class 1, and now we want to go through every word in rhyme class 1, because they could have rhymed with each other, and figure out the number of ways we can form a word that ends in rhyme class 1. So we'll have long count store the number of ways we can do this, and we can do a for each group by doing for each syllable count in our array list of longs of pair.getValue. And remember, pair.getValue stores the array list that we created earlier in our code that stored rhyme class to the number of syllables. So now we want count to plus equal ways to add, dp ways to add of k. Remember, there are k syllables per line, and we're using the last syl amount of syllables to be the last word in that line. And we want to take this mod just to be safe. Remember, it's better to be safe than to be sorry. And we can take count mod equals mod. Finally, we want to raise dp letter of I to the power of how many ever there are of it. So we do this by doing dp of letter of I equals mat.pow of count and let.get the character of whatever we are looking at right now, which is I plus A. Now, there is a slight issue that arises with this, and that happens because we have to take it mod. Now, obviously, we could try saying, okay, let's take it mod at the end here, but that just doesn't work. For example, let's say the amount of A's we had is like 200, and count is also 200. 200 to the power of 200 is way too big to store in any value that we have in Java, and will in fact just overflow error and cause a lot of issues to our code. So what we have to do is we have to implement our own exponentiation algorithm. And we can use exponentiation by squaring, which I like to call exponent by square. Now, obviously, we have to implement this code later, but let's first get the gist of our code down first before we implement that code. So we need to add in the amount that has been squared because we need to add in a number of ways it could be done with letter 1, letter 2, and so on and so forth. Finally, since we are making this recursive and be like the first amount of letters, so we want dp letter of 2 to store the number of ways you can do A, B, and C, not just C, we need to multiply whatever dp letter of I is by whatever dp letter of I minus 1 is. And obviously this will fail when I equals 0. So let's take care of the case when I is not equal to 0. Because if I is equal to 0, then we just leave dp letter of I as is. But if I is not equal to 0, that is when we are able to do this multiplication. Now before we move on, let's add a few mods, because if we don't do this, we might integer overflow error. And it's just easier to have the mods here, so we know that we are multiplying correctly. Now, we also have one more case to consider, and that is the case where the letter that we are looking for was not contained in our poem. And if that line is not contained in the poem, what we want to do is set dp letter of I to be equal to dp letter of I minus 1. And this is because if I don't find a C, then the number of ways to make the poem with lines A, B, and C is the same number of ways to make the poem with lines A and B, because there are no C's in our poem. But once again, this code fails if I equals 0. So we have to check if I is not equal to 0. Then we are able to do this. Otherwise, what we do is we set dp letter of I, which will be 0, to 1. And this is because since our program uses the last state and multiplies it, we don't want it to be 0 because then all of our future states will be 0. We just set it to 1 because there are no ways to do it. So finally, what we need to do is we need to print our answer. And what we'll end up printing is dp letter of 25. Because since there are 26 letters in the alphabet, the number of ways we can make our poem is the number of ways we can fix lines A, B, C, D, all the way till Z. And then finally what we do is we close our print writer so that we can submit our code with a non-empty file. So now let's take a look at the exponentiation by squaring code. Now the way exponentiation by squaring works is that by using a mathematical trick, it reduces the time complexity of squaring really large numbers to log n. And this is done by basically saying if the exponent that we're raising k to is even, then we can say that as k to the power of 2n, k to the power of 2n equals k to the power of 2 to the power of n. And this actually helps us reduce the time complexity because we're taking it modulo this large number. So first we want to tackle the base cases of if our exponent is 0, then we want to return 1. And if our exponent is 1, then we want to just return k. And we'll just take it mod to be safe because we are squaring very large numbers. So if none of these conditions are met, we want to use that trick we saw earlier of else if exponent mod 2 is equal to 0. So our exponent is even. Then we want to return this function, because it's recursive, of k times k mod to be safe, and then exponent over 2, and we want to take that modulo. Otherwise, if the exponent is odd, what we do is we write this as k times exponent by square of k times k mod exponent over 2 mod, and we also want to take k mod. So the reason this works is because, like we saw earlier, it works with even exponents, but what happens when we use odd exponents? Well, if we have k to the power of 2n plus 1, this can be written as k to the power of 2n times k, because k to the power of 1 is 1, or k. So we can essentially use this property to break it down even further. Now let's try submitting this onto the USACO grading server. As you can see, it ran in the time allotted and it got full credit.